Magnetic effect of electric current. This is the topic of our discussion. In the previous chapter, electricity, we have learned lots of properties associated with electricity. In addition, the heating effect of electricity. In this chapter, we are going to discuss about the magnetic effect of electric current. That is, using electricity, how we can make magnetic effect, that is in the absence of magnets. And you know very well, using magnet only we can produce magnetic effect. But in the absence of magnet, with the help of electricity, we could make this. And in this chapter, it is going to be discussed how the electricity and magnetism is related. That is, in olden days, it was believed that electricity and magnetism are the two different fields of subjects which could not be related with each other. But it was Hans Christian Oersted, with a simple lab experiment, accidentally discovered the relation between electricity and magnetism, leading to the concept of electromagnetic effect. Hans Christian Oersted once, what he did is, he just made a simple circuit and accidentally he placed the magnetic compass close to the circuit. And while he was engaged with the circuit working, he found that when the electricity passed through the circuit, the magnetic compass needle showing a deflection. Let us go through this activity with the help of the diagram. That is, consider this is your simple circuit, battery, and you got a resistance wire, and this is your straight wire. Okay? Such a way, if you put the key, your current will flow through the circuit. And he got the magnetic compass here like this. And you know very well, magnetic compass is nothing but a device using which you can identify direction, because the needle which is found inside the magnetic compass itself is a magnet. It is made of magnet and it has got the north pole as well as south pole. And how it is used, any idea, what is the reason, what is the principle behind the working of magnetic compass? That is, Earth itself is a magnet, right? And since Earth itself is considered as a magnet, you can treat one end of the Earth as one north pole and the other end as south pole. See, this is our Earth, treated as magnet, and you know very well the direction. This is north pole, this is south pole, geographic north pole and geographic south pole. If you consider Earth itself as a magnet like this, see, such a way, this is south and this is north. And if you hang a simple bar magnet, what it is going to do is, it is going to get attracted towards. See, if I place a magnet, simply hang it, you know very well that like poles attracts each other and unlike poles repels each other, right? Unlike poles attracts each other and like poles repels each other. So if you hold a simple bar magnet, what it is going to do is, its north pole, it is going to get attracted towards the south pole, magnetic south pole of my Earth's magnet, whereas the north pole, the south pole of my bar magnet is going to get attracted towards the magnetic north pole of the Earth magnet, right? So here, if I hang it, it is going to stay itself finally like this, such a way, this end is going to be north, this end is going to be south. This is why, what is the reason behind it? The north pole of the simple bar magnet getting attracted towards the south pole of the Earth's magnet. Similarly, the south pole of the simple bar magnet getting attracted towards the north pole of the Earth's magnet. And this is, from this settlement, we make a conclusion, that is, the magnetic south represents the geographic north. Similarly, the magnetic north represents the geographic south. Fine? So any magnetic material, if you make it to rotate freely, you will find it will finally settle down such a way pointing the north-south direction because it is responding to the Earth's magnetic field. And the same thing is going to happen here. So this is, if you keep simply a bar magnet, this will be the final settlement, that is north and south, pointing like this. But once you put the key, what is going to happen? The current is going to flow through the circuit like this, and you will find that is, this deflection is not maintained like this, but taking a new position like this. Fine, showing a small deflection. And when he reverses the battery like this, such a way, now the current is going to flow in the reverse direction like this. Fine, and this time you will find a deflection exactly in the opposite direction. So this laid an idea, this gave a concept to the Hans Christian Oersted, the scientist who worked actually behind it, that the current carrying conductor is also producing some magnetic field around it, and responding to which the magnetic compass needle is showing the deflection. Fine, that is, you can expect the magnetic compass to undergo deflection only in the presence of an external magnetic field. Fine, it should come in contact with any other external magnetic field. Then only you can expect. Magnetic field means some magnetic experience. So it could be made a conclusion that this current carrying conductor itself is behaving like a magnet with the magnetic fields around it, and when this magnetic compass needle placed in this magnetic field, it started showing the deflection. And this is what known as electromagnetic effect, which lead to the concept of the relation between that electricity and magnetism. They are not separate topic of subjects, but they are well related with each other. And the similar reverse phenomenon is also there, that is using magnetic effect, that is using magnets, we can even produce electricity. They are actually interrelated with each other. In the absence of magnet, using electricity, we can produce magnetic effect. Similarly, without using any electrical supply, using a magnet, we can produce electricity also. And this is the topic of a discussion. This is what we are going to discuss in detail throughout this lesson. So the next topic is about magnetic field and field lines. So what is magnetic field? The very beginning, let's see. That is, if you take a simple bar magnet and place it over a cardboard or some other heavy material and sprinkle the iron filings over it and tap it. This is a simple experiment which you have done in the lower class. And what is observation made out of it? You'll find that the iron filings get aligned themselves in a particular pattern, showing a particular representation, which actually known as magnetic field. So in the definition, this could be said as magnetic field is nothing. It is the region around a magnet over which the magnetic force could be experienced. And you can't experience, that is this strength, that is determining the strength of the magnetic field. This magnetic field actually represents the field of force of magnet. That is, only in this region you can experience the magnetic effect, strictly following a certain pattern. And this could be, that is, if you go for the iron filings, you will find that simple bar magnet, north and south. If you sprinkle it, you will find that they are just getting themselves aligned like this, right? And here very much crowded, and they are very much crowded. This is a simple arrangement they are expected to take place. And this pattern we could draw, we could make out, we can trace out with the help of a compass. That is the next activity. That is, take a simple bar magnet and take a compass. Just place it close to the one end of this bar magnet. So initially it would have, that is, if you had kept the compass needle somewhere far away, this would have been the position north and south, settling down in the north south. Since it has been brought near another external magnetic field, because of its influence, it is not going to stick around with this. That is, this is a response to the Earth's magnetic field. Now, since it is experiencing in addition some of the magnetic field which is quite stronger compared with the Earth's magnetic field, it starts to respond to it. So, greater force towards which it is getting influenced. And here again, it is going to show a pattern like this. That is, the south pole attracting towards it and the north pole pointing in the opposite direction. What you have to do is just take this point and keep the compass exactly in this position. And again you will find that the needle is going to settle down like this. This as south and this as north. Again keep here. So you will get the pattern like this. It's a very simple activity. If you do it, you can make out, you can trace out. That is, every time you keep the compass at the extreme end where in the previous position the needle was actually pointing. So finally you will get a pattern like this. That is, if you make out, finally you will get the pattern like this. So similarly, anywhere if you place, you will get a separate line of path representing the direction of that is the formation of the field line or the path of the field lines. Okay, so here this is what known as magnetic field. That is the region around the bar magnet where you can experience a force of magnet, and the lines, the traced out lines, actually known as the field line. So I'll just rub this and I'll show the field line pattern. That is the final pattern how we are going to expect. This is the shape of the magnetic field line. See, while drawing the magnetic field line, you have to be very careful. That is, no two field lines should intersect with each other. And here, as I told you, with the help of the compass actually we traced out, and this is conventionally considered, that is took as the direction of the magnet. See, magnetic field actually, it is a vector quantity which has got magnitude as well as direction. So its direction is very important. So generally, conventionally, it has been declared or accepted that the simple bar magnetic field as from north to south outside the bar magnet and south to north inside the bar magnet, like this. See, like this. Okay, this diagram, while drawing this diagram, these are things which that is, you have to draw the field lines such a way it moves from north to south, and no two field lines should intersect each other. I am coming to that point. That is, if you consider a magnetic field pattern like this, that is, in this point you got an intersection of two field lines, right? Which means that if you keep a compass needle here, the needle should either point towards this direction or towards this direction. That is not going to happen because the needle strictly will follow a single path, right? So the point of intersection is impossible, since you can't expect the magnetic compass placed at that particular point to point in two different directions. So we make a conclusion, that is, it is impossible to have a intersection of field lines. That is, no two field lines are expected to cross each other. That is, it is believed that only based on assumption it is all, that is, since you can't expect the compass needle to point in two different directions, it is declared or it is accepted that no two field lines are going to cross each other. That is, it is treated as a field line which starts from here, goes in a loop form, and it completes. It is actually a closed curve. That is, each field line makes a closed curve. See, this is the path of the single line. Similarly, if you consider, it begins from here, it goes like this, it gets completed like this. So each and every field line, magnetic field pattern is expected to have this, that is, continue with this closed curve. That is, these are the important properties. The first property of the magnetic field line is that The field lines are running from north to south direction outside the bar magnet and south to north inside the bar magnet. Fine. And the second important property is that no two field lines will cross each other, because if there is such a point, you need the magnetic compass needle to point in two different directions. Since it is impossible, so we can declare no two field lines are expected to intersect each other. Third important point is that you'll find that the field lines are mostly crowded near the poles, whereas they are very well spaced from each other when you move away from or near the body of the magnet. This again leads to an important concept, that is the density of the magnetic field actually determines the strength of the magnet, that is magnetic field. That is, greater the density, the more crowded field lines represent the stronger field over that point. So it was concluded that near the poles the field lines are more stronger, that is the magnetic effect is going to be more strong compared with the near portion. That's why if you bring any magnetic material close to it, you'll find them getting attracted towards the pole rather than the body of the magnet. Though the body itself has got the magnetic effect, it is going to show the greater, stronger field only near the poles. And this is determined based on the magnetic field. That is, the more the number of field lines or the more densely populated region represents the stronger field region. So near the poles they are expected to show the strong field. And then close to curves, that is each magnetic field lines are actually close to curve, that is there is no any break in between the path of the single magnetic field line. So these are the important properties about the coming under the topic magnetic fields and field lines.